Okay, we'll continue with our study of the deformation gradient f and its effects. In the last segment, we looked at how it induces the notion of stretch and strain, right? And we defined a stretch tensor and a strain tensor. In this segment, we're going to take the idea of the effect of f further. We're going to look in particular at ways to decompose f, which will tell us more about the nature of deformation. Okay, so the topic of this segment, and most likely the topic of the next segment as well, is the polar decomposition of f. So here's the idea. We have f equals the partial of phi with respect to capital X, with respect to the reference placement. Now we may ask the question, are there ways to write f as the product of two tensors? And this may seem like a random, arbitrary mathematical question, but it turns out to have great physical implications, right? In particular, we're going to ask, can we write f, okay? Can we write f as follows, right? Can we write f as the product of a tensor R and another tensor U, where R is a rotation tensor? Mathematically, that means R belongs to the space that we introduced a few segments ago called SO3. It's a rotation tensor, it's orthogonal, which implies that, remember, this implies that R transpose R equals the identity matrix or the isotropic tensor, which is also the same result that you get if you consider RR transpose. There is another result for R, which we haven't mentioned so far, but which really follows from the result we've just written down, which is that the determinant of R equals plus or minus 1. Okay? R is a rotation tensor. Okay, so can we write f is equal to Ru, where R belongs to SO3, it's a rotation tensor, and U equals U transpose. U is a symmetric tensor, right? Now, because we are going to come across symmetric tensors quite often in our study of continuum mechanics, and we've already seen two in the previous segment, we are going to introduce some notation for it. We are just going to say that U belongs to S3. S implying symmetric, 3 implying 3 dimensions. Okay, so this is the question we are asking. Can we write f as this product Ru in that particular order? Okay, where U is symmetric and R is a rotation tensor. Okay, the answer is yes. Okay, the answer is yes. And in fact, f equals Ru comes with a name. This decomposition is called the right polar decomposition. Right? It's the right polar decomposition of f. The way I'm going to proceed now is to demonstrate certain mathematical properties, and then we'll come back and look at what this means physically. Okay? So let's look first at these mathematical properties. So what we've done here is to essentially postulate that this decomposition exists. Okay? We need to sort of demonstrate mathematically that yes, it does actually work. You can actually write this. Okay? So let's start out by assuming that this decomposition does work. Now, what I'm going to talk about over the next few minutes is essentially a series of mathematical proofs, but I'm not really going to set it up in the fashion of the statement of a conjecture and its formal proof, right? I'm going to demonstrate things which will amount to a proof, however, right? And so it's going to be completely rigorous, okay? All right. So here's how we're going to proceed. We've decided that U is symmetric, okay? So if U is symmetric, we have the following, right? Since U belongs to S3, right, which means U is symmetric, what this implies is that from the standard eigenvalue decomposition of U, okay, what this implies is that the eigenvectors of U can be made orthonormal, and that the eigenvalues are real. Okay? So let's write that. What this implies is that the eigenvalues of U are real. Okay, they are real numbers. And let's denote those eigenvalues as lambda, lambda 1, lambda 2, lambda 3. These belong to reals, okay? And the eigenvectors can be orthonormalized. And recall what orthonormalization means. It means that if the eigenvectors n are n1, n2, n3, corresponding to the three eigenvalues, so it means that if n1, n2, n3 are the eigenvectors corresponding to lambda 1, lambda 2, and lambda 3, then we know that ni dotted with nj, where I and j run over 1, 2, 3, is equal to the Kronecker delta. Okay? And this comes just from our study of eigenvalue problems. We're not going to go into that detailed study of eigenvalue problems. We're essentially going to use those properties. From that eigenvalue decomposition and the standard eigenvalue problem and these two results that I've just put down, another result follows. Okay. Also, there is, just like the eigenvalue problem, it's sort of a corollary of the eigenvalue problem. There is another sort of decomposition that one can write for U, and this decomposition is inherited from the eigenvalue problem, and this is that there is a spectral decomposition of U. And that spectral decomposition is that U is the sum I going from 1 to 3 of lambda I multiplying the tensor product of each eigenvector with itself. This is a result that I assure you you've used at some point if you've ever worked with a standard eigenvalue problem. Okay, you've used it in some form or the other. Okay, so we've assumed that we've said let's suppose that there exists a U. Well, if there exists a U, we can write it in this fashion. Okay, what else can we say now from here? We haven't yet demonstrated unequivocally that a U exists of this form, okay? But we're just going along with the game so far. Okay. All right, we note this result. Then we say, well, but wait a minute, I can recall that I can write, recall that F transpose F equals C. C is symmetric, as we demonstrated in our previous segment, and C is positive definite. That's my abbreviation for positive definite. Okay, we proved this in the previous segment. Okay, if this is the case, let's now put in this our assumption for the polar decomposition and see what this gives us. So our F transpose becomes RU, the whole transpose. F is just RU, which is now using the fact that the transpose of a product is a product of the transposes, but in the reverse order, we have this. But R is an orthogonal tensor, right? It belongs to SO3, which means that this product is the isotropic tensor. As a result, we have this equals U transpose U. But then U belongs to symmetric, is a symmetric tensor. So this is just U square. Okay? So what we've demonstrated that C is equal to U square. Okay, what we've demonstrated is our Wright-Cauchy-Green tensor is just U square. If a U square exists, this has to hold. Okay? All right. But now remember, C is symmetric, C is positive definite. If C is symmetric, it also admits its own spectral decomposition. Okay? But C belonging to S3 and positive definite implies that we can write C also as a spectral decomposition, some I going from 1 to 3, okay, of its eigenvalues, okay, times its eigenvectors, right? So, since C is symmetric, its eigenvectors can also be orthonormalized, right? So what we are saying essentially is that we have for C this form. I know I haven't yet written out the eigenvalues, but I'm going to do that in just a second here. Okay, this comes from the fact that there is a spectral decomposition for C. Okay, my abbreviation for decomposition is decomp. I haven't yet put in the eigenvalues. C is positive definite. What do we remember about the eigenvalues of a positive definite tensor? What are the eigenvalues? Think about it for a second. They're positive. Okay? If the eigenvalues are positive, I can write them as squares, right? Because squares of real numbers are positive, right? The eigenvalues of C are real because they're symmetric. They're positive because C is positive definite, which means I'm allowed to write these eigenvalues as, let me just call it lambda sup C. That is just to remind us that these are the eigenvalues of C, not the eigenvalues of U. Lambda Ci square. Okay, that square that I've written represents each eigenvalue of C because it is positive definite. Okay, so what I've done here is also use the result that because C is positive definite, the eigenvalues of C are real and positive, so write them as lambda Ci square. Okay, that quantity that I've just written represents each eigenvalue of C. Okay, of course, I going from 1, 2, 3. All right. Okay. Fine. So we've got this far. Let's go back to U. Because of the way we wrote U, we can now write U square as sum over I. Actually, I won't use the sum over I. Let me write it out explicitly because I want to demonstrate something here. Okay. U square is lambda 1 n1 tensor n1, and I realize I'm saying one thing and writing another, so I need to be a little careful here. Plus lambda 2 n2 tensor n2 plus lambda 3 n3 tensor n3, that is U, and I'm going to multiply it by another U, which I'm going to write on the next line simply because I've run out of space there. Lambda 1 n1 tensor n1 plus lambda 2 n2 tensor n2 plus lambda 3 n3 tensor n3. And I also caught another typo, which is that I have a lambda I here. It needs to be a lambda 1. Okay, this is what I have. Now recall, the n1, n2, n3s are orthonormal. When you carry out this product, therefore, what you're going to see is that n1 dotted with n1 is going to give you 1. But n1 dotted with n2 is going to disappear. It's going to give you 0. n1 dotted with n3 is going to disappear. Likewise for all the other products. So when we carry this product through, what we are going to see is that U square is essentially equal to lambda 1 square n1 tensor n1 plus lambda 2 square n2 tensor n2 plus lambda 3 square n3 tensor n3. Okay? All right? So now let's compare. With C, which we wrote as sum over I equals 1 to 3, lambda C I square. Now, I wrote Ni tensor Ni, and you may have thought that I already knew for some reason that this is going to be that the ends are going to be the same between C and U, but we don't need that. Let's suppose that we just had NCI as the eigenvectors of C. When you compare the two of them, okay, and given the fact that the spectral decomposition is unique, because the eigenvalue decomposition is unique, okay, what follows is, since the spectral decomposition is unique, okay, and this is unique because the eigenvalue problem is unique, right? The eigenvalue decomposition is unique. When you compare U square and C, and we saw that if U exists, we've got to have U square equal C. So when you compare the first two lines of this slide, what the only conclusion you can have is that the eigenvectors of U are the eigenvectors of C. Okay. Okay, and furthermore, lambda I, each lambda I of U equals plus or minus lambda Ci. Okay? What we are going to do is pick the positive eigenvalues. Okay? So we will choose lambda I equals lambda C, sorry, equals the positive value of lambda Ci, right? For I equals 1, 2, 3. But now observe what we've done. We've essentially said that the eigenvalue of u, the eigenvector of u is the same as the eigenvector of C, and the eigenvalues of u are simply the positive square roots of the eigenvalues of C. Now we know that the eigenvectors of C exist. We know that the eigenvalues of C exist, that they're positive, they're real and positive. Well, what this means is that the eigenvalues of u exist, the eigenvectors of u exist, but a tensor cannot exist without, we cannot have a tensor that has eigenvalues and eigenvectors existing and the tensor itself not existing, right? We've essentially proved that u exists, right? Okay, which implies that u equals sum over I lambda I ni tensor ni exists. Okay? U exists. We've proved, therefore, that U exists. U belongs to S3. And because of the way we've chosen the eigenvalues of U to be positive, it implies that U itself is positive definite. Okay?